Okay, so we got another Mathematics Olympiad problem. Can't remember which year this paper's from, but it'll be in the title. We're going to follow a very similar format to the last video, where we're going to run through the solution given in the mark scheme. We're going to make some comments on the method, and yeah, I mean, really, as you look through this solution, you should be using it. Should be some good practice for you. If you want to pause, try this problem now. That's written on screen, go for it, and then we're going to run through the solution. I'm by no means some sort of expert with all the answers on how to do Olympiad papers, but hopefully there'll be some useful tips in here. So let's get into this problem. So we've got A0, A1, A2, so on, positive integers that are in a sequence satisfying this rule. So the sequence is defined based on the previous term, so an plus 1 is equal to the square root of an if the square root of an is an integer, so that's simple enough. And then if the square root of an is not an integer, then the next term is defined by just adding 3 to the previous term. So that's not an plus 3, that's an plus 3. Our job is to determine all values a0 greater than 1, for which there is at least one number such that an is equal to a for infinitely many values of n. So essentially we're looking for starting values of the sequence that mean that there's a number in the sequence that repeats over and over again. So what does that really mean? Because this is what's going to help us solve the problem. Well, that means that the sequence eventually becomes periodic. Okay, so that simplifies the problem a lot, because now we know what we're looking for. We're looking for values of a0 such that the sequence will eventually become periodic, and we're going to get into that now. So first we consider the case where a0 is, or an, just any sort of an, because it doesn't really matter. So if an is congruent to minus 1 mod 3, well, a square cannot be congruent to minus 1 mod 3. Excuse the slightly questionable notation, but we'll just talk through this now. Essentially, if a number is congruent to minus 1 mod 3, when we square it, it's congruent to 1 mod 3. Okay, just standard rules of number theory. If a number is congruent to 0 mod 3, then its square will also be congruent to 0 mod 3, and in the case where a number is congruent to 1 modulo 3, its square will still be congruent to 1 modulo 3. And a number either has to be congruent to minus 1, 0, or 1 mod 3. So in all those cases, the square is never congruent to minus 1 mod 3. And essentially what we'll then argue, and without writing this out formally, we'll have to guess, is that any an congruent to minus 1 mod 3 implies an plus 1 is equal to an plus 3, because we know this, the square root of an is not going to be an integer. We just discussed that now. And that's greater than an, and that's going to be true for all terms. So if a0, we're essentially then going to argue if a0 is congruent to minus 1 mod 3, the sequence is strictly increasing. It's going to increase by 3 every single time, because each an is going to be congruent to minus 1 mod 3, because we're adding 3. Okay, so that's what I forgot to write, that an plus 1 is going to be congruent to minus 1 mod 3 still. Okay, so this sequence is never going to turn out to be periodic, so any a0 such that it's congruent to minus 1 mod 3 can be excluded now. We don't have to consider those anymore. We know that none of those are what we're looking for. So now we're going to consider when an is not congruent to minus 1. We're going to do a little bit of pre-work on this case, and then we're going to consider the particular cases where an is congruent to 0 mod 3 and 1 mod 3. and see if any of these give us periodic sequences. So we're going to run through this work, and then when we use this preliminary work later, we're going to retrospectively justify it. So if an is not congruent to minus 1 mod 3 and an greater than 9, and this is the bit that we're going to justify retrospectively, because in the cases where an's less than 9, we can sort of work through those individually, and then when we want to prove in more generality results later down the line, we're going to need this result for an greater than 9. So we're going to let t squared be the largest perfect square, so t squared is a perfect square and t squared is less than an, so it's but it's also the largest perfect square, less than an, so any s squared, say less than an, is less than t squared. So since an is greater than 9, t is greater than or equal to 3. Okay, so that should be pretty obvious. And then, so the first square that actually appears in the sequence, okay, remember how we define the sequence, an plus 1 is equal to square root of an, if the square root of an is an integer, or an plus 3 in any other case. So the first square in the sequence, an plus 3, an plus 6, so on, will be either t plus 1 squared, t plus 2 squared, or t plus 3 squared. Let's add that in. The next square will be one of these, okay? So therefore, there's an index m greater than n, so a term further along the sequence. So there's this term further along the sequence such that am is less than or equal to t plus 3, which is less than t squared, and that's because t is at least 3, which is less than an. Okay, so that's nice. So essentially what we're saying is, if an's greater than 9 and an's not congruent to minus 1 mod 3, we will get to a point where we get a term that's less than an, essentially. So now if an is congruent to 0 mod 3, then an plus 1 is also a multiple of 3. So if an is in the set 3, 6, 9, and we're starting to see that retrospective justification we're talking about, the sequence follows the pattern three, 6, 9, and the square root of 9 is 3, so 3, 6, 9, and so on. Okay, so if a naught's in any of those values, we get what we're looking for, we get some periodic sequence. Now we're going to look at if an is greater than 9, but it's also a multiple of 3. So if an's greater than 9, we're going to let j be an index such that AJ is equal to the minimum value of the set AM plus 1, AM plus 2, and so on. So it's the minimum value of the term of the set of terms in the sequence. We must have AJ less than or equal to 9 if AJ is the minimum, because of the claim before about there being some AN less than AN. Okay, so if AN is greater than 9, there's some AN less than 9 from before, and because AJ is the minimum of this set, this AJ must be less than 9. Okay, and so therefore AJ is in this set 3, 6, 9. So we get this periodicity again, alright, which is what we're looking for. So even if our initial term starts outside, we end up in this loop of 3, 6, 9 over and over and over again. So finally, we're going to suppose that AN is congruent to 1 mod 3, and we're going to do a similar thing here. We're going to consider all the individual cases less than 9, and then the ones over 9 we're going to generalize. So obviously if 4 was the first term in our sequence, this goes to 2, which is congruent to -1 mod 3, and then once we've got to something that's congruent to -1 mod 3, that's our new starting term of the sequence, because the sequence only depends on the previous term. There's no memory. So once we get to this point, we can then apply everything we did in the first part of this problem to what we were saying about the case where A0 is congruent to -1 mod 3, or any AN is, and therefore this is non-periodic. Okay, so that case is done. Suppose AN is equal to 7 at some point. Well, this goes to 10, goes to 13, goes to 16, goes to 4, goes to -2, congruent to -1 mod 3. We apply exactly the same logic. Done there. So now for AN greater than or equal to 10, or just greater than 9, because we're of course dealing with integers. Again, we do a similar trick to last time. We take j greater than n such that AJ is equal to the minimum value of the set of terms in the sequence. So what we want to prove essentially is that, just like before, we want to prove that AJ must be congruent to, well, actually we're just trying to find that out, but that's eventually what we what we get to. We know that if AJ is congruent to -1 mod 3, then just like before, we're not going to get any periodicity, and so yeah, we're going to investigate that now. So what we're going to do is we're going to suppose AJ is congruent to 1 mod 3. Okay, we must have AJ less than 9 by the minimality of AJ and the preliminary work we were doing. So it follows that AJ is in the set 4 to 7, but that means both of these we know maps to 2, so there must be some AM equals 2 less than AJ for some m greater than j, and that means that aj is not the minimum, even though that's what we defined aj, so that's not possible. So we must have aj is congruent to -1 mod 3, and in that case we don't get this periodicity. And ultimately, after all this work, we come to the conclusion that the sequence is, we'll write out some sort of closing statement. We can see that the sequence periodic if and only if a0 is congruent to 0 mod 3. So ultimately the values of a0 that we're looking for is the set of all multiples of 3, and that's our answer. Okay, so just like last time, we'll comment on the method. The reason we ended up looking at modulo 3 quite a lot is because of the definition of the sequence. If we're looking at adding on 3, that gives us an idea to try with this number theory problem working modulo 3, because we can have some sort of relationship between current terms and the next terms, and we'll know the next terms congruent mod 3 still, which proves to be quite useful. In terms of the preliminary work, I guess as you start to work with the cases of an equal to 0, you can see that the cases 3, 6, 9 are simple, and the same with -1. You can see 4 and 7 are simple as you start to work through those individual cases, and then that's where that preliminary work comes in. I think this is quite a tough problem, so I wouldn't worry if you didn't get too far with it. But again, let me know in the comments if you had a different way of doing this. This is the method that's in the solutions, and if I didn't make any parts of this particularly clear, because I'm just sort of skimming through the solutions, then let me know in the comments and I will try to clarify that for you. So anyway, thank you very much for watching. I hope to see you in the next video.